So we were solving this equation, and spherically symmetric and static solution of this equation we have found to be like this: C2 over R dt squared minus dr squared divided by 1 plus C2 over R minus R squared d omega squared. Here C2 is some constant which is independent of t and r and angles, and we want to find the physical meaning and the value of the C2 right now for the given situation. So we observed that this metric, as r goes to infinity, this term becomes smaller and smaller, and we arrive at flat space-time. So let us use this. Let us consider non-relativistic particle very far from the gravitational center. It means that we want to consider that its velocity, so the trajectory of the particle, or world line of the particle, is t and z of t. This is the world line of this particle, z mu of t. And so when it is very far from the gravitational center, we know that its action, from classical non-relativistic mechanics, we know that its action is proportional to minus m integral 1 minus z dot squared over 2 of unit mass plus v of z modulus dt. So let me stress again. So we consider, no, not unit, a particle of the mass m interacting with this gravitational center very far from it and for very slow velocities. So we consider that z dot is much less than 1. So this is approximation of the relativistic action. Approximation because like this term contains the trivial contribution. And this guy is nothing but the Newton potential. It means that V, function of Z, which is the same as V as a function of R, is Newton potential minus kappa m over R, where m is the mass of the gravitating center. So we know that the action, actually relativistic action, should be equal to this. And this is just its approximation when we are very far and for slow velocities. Then from this and this we have approximate relation that ds is approximately equal to 1 minus z dot squared over 2 plus v of modulus z dt. So this approximation is valid as r goes to infinity and z dot modulus is much less than 1. Now, to linear order at z dot squared and v, to linear order in v, we can square this to obtain that ds squared is equal to, approximately again, equal to 1 plus 2 v of r dt squared minus z dot squared dt squared. But this is equal to 1 plus 2v of r dt squared minus dz squared. So we have the following relation for the metric when we are very far. Then we have to have that GTT component of the metric, so this component of this metric, has to have the following form. 1 plus 2 v of r, which is 1 minus 2 kappa m divided by r. Now, to have this to be true, we have to have that C2 is equal to minus 2 kappa m. Minus 2 kappa m. It has also the other name, Rg, and it is called as a gravitational radius for the given mass m. Thus, the metric under consideration has the following form. ds squared is equal to 1 minus Rg divided by r dt squared minus dr squared divided by 1 minus Rg divided by r minus r squared d omega squared. So this is the metric which solves Einstein equations and describes spherically symmetric gravitational field created by a massive body of the mass m around itself.